Hello, welcome to our next lesson on Bohr's model of the hydrogen atom. Let's start off with a little bit of history. In 1913, Niels Bohr proposed a model of a hydrogen atom based on its emission spectra. So, looking at the emission spectra, like we did in our last lecture, he came up with his idea for how atoms worked and functioned and how they were formatted. Here's a picture of him on the right, just to know what he looks like. He made this to overcome the main problem of Rutherford's model of an atom, which you may have heard of Bohr-Rutherford's before, which is kind of putting their two ideas together in the model that we've seen. And his main idea that electrons would orbit around the nucleus, quickly lose energy, and then fall into the nucleus. But we know that electrons never end up in the nucleus, and that is because of the work of other people after Rutherford. Together, they make the Bohr-Rutherford model, like I mentioned, and you've definitely seen before. He proposed three main postulates for his theory, or his model. The first is that an electron can only exist in certain stationary orbits around the nucleus, and these orbits are associated with discrete energy levels. So, what this means is that electrons can only be found in specific spots around the nucleus, which he calls as energy levels. So these different energy levels would be like n equals 1. So the first energy level, which orbits around the nucleus, then the second energy level. Electrons could never be found in the middle. They could only be at the first one or have moved all the way up to the second one, or moved all the way up to the third one, and so on and so forth. Electrons could never be outside of these energy levels. It just wouldn't how they work, unless they were moving between the two of them. The second is that when an electron in the orbit with lower energy level absorbs a photon of the right energy amount of energy and moves to a higher energy level and remains at that level for a short amount of time. Inversely, when the electron returns to a lower energy level, it emits a photon of light. This photon represents the energy difference between the two levels. So, for example, if a electron on the third level moved down to the second level, it would emit a specific photon of energy that was the difference between these two levels. If an electron were to go from the second level to the third level, it would have to absorb a photon of light that was the same amount of energy as the one it would emit, going from back and forth. That could be the same. An electron could go straight from the first to the third by absorbing the right amount of energy, but it could never get anywhere in between the second and third, because that's just not one of the energy levels that the electron could exist at. He got to this theory by observing hydrogen's emission spectra. So if you look at what we have here, hydrogen has four specific bands. And as it turns out, each of these four specific bands correspond to when an electron emits, when it returns to the second level of energy. So for example, it gives this orangey color when a third energy level returns to a second energy level. It gives this green color when a fourth energy level returns to the second energy level, and so on and so forth. What the element is emitting during its emission spectra is those specific photons of energy that are given off by an electron to going back down to lower energy levels. So, what we can say is that electrons moving between each energy level are defined by discrete quantized values of energy, or photons. We can define these values as quantum numbers, which in this case, quantum numbers can only be integers or half integers. This quantum number that we're talking about here is the principal quantum number, or n, and it can only be positive integer values, where the greater number means higher energy level. So basically what this means, the principal quantum number is our energy levels. So n equals 1 will be the first energy level of an element, n equals 2 will be the next. There can never be a 1.5. An energy is either at energy level 1 or it's at energy level 2, or obviously higher, but you understand what I mean. And there's no negative energy levels. It can only be increasing. And the higher numbers indicate it as a higher energy level. What we can also see, so that was the visible light. When we take any electron returning to the second level, it emits a visible light. But that's what we can see physically, or with like our own eyes when making emission spectra. But as it turns out, at different levels, we see different electromagnetic wavelengths. So when any wavelength goes from a number to the third energy level, that actually emits infrared radiation because it is a smaller difference, so less energy, bigger wavelength makes infrared radiation. When something travels to the first energy level, because it requires a lot more energy to go there, smaller wavelengths, it actually is UV radiation. So we can think about just a recap of what I said. When anything n greater than 1 traveling to 1 is UV light, anything n greater than 2 traveling to n equals 2 is visible light, and anything greater than 3 traveling to n equals 3 is infrared light. That will be emitted by the atom. Energy levels closer to the nucleus can hold fewer electrons. The maximum number of an electrons in energy level n, like we talked about, the principal quantum number can hold is 2n squared. For example, when n is equal to 1, it can hold 1 squared, so 2 times 1, which is 2 electrons. When n equals 2, it can hold 2 times 2 squared, which is 4, so 2 times 4, 8 electrons. When n equals 3, it can hold 3 squared, 18 electrons, and so on. You can think about it in our Bohr-Rutherford diagrams. On the first energy level, you can put 2 electrons, and on the second energy level, you can have 8 electrons. So you've seen this idea before. Obviously, we have since found out that some of Bohr's ideas are incorrect, but the things he's put about energy levels, for the most part, are very accurate. In our next lesson, we'll learn about the quantum model of an atom, which is more accurate or more what we believe today. But this was Bohr's model of an atom. And thank you for listening.